Hello, welcome to part 2b of this series of videos about the moment of a force or torque. In part 1 we covered some background. Part 2 was going to be too long for a single video, so it's split into two parts. 2a was about the centre of gravity and how to use it in moment calculations, and part 2b, which is what you are watching now, is how to use the principle of moments. As we work through, there'll be some examples for you to try for yourself, so you should have a pen and paper. A calculator is optional, the arithmetic is very simple. Let me go over what we'll be covering. Some background first, how to add moments, how to use a sign convention for adding moments, what we mean by the algebraic or vector sum of moments, and what we mean by the term rotational equilibrium. Then we'll go on to talk about the principle of moments itself, definition or definitions actually, and how to use it. Let's start with adding moments. We can add or in fact subtract moments, providing they are moments about the same point. Now, to make that clearer, let's do it. So there's a plank, an object in yellow. Let's mark a point on the left, P. Let's put two forces on it. I'm not saying the thing is in equilibrium, I'm just saying there are two forces on this object, a 20 Newton force and a 30 Newton force at the positions shown. And the question is this: what is the total moment of these two forces about point P? How do we combine the two separate moments? Now, if you want to try this for yourself, you can pause and think about it and try it for yourself now. Well, I hope you've had a go. Pause the video if you needed to. Let's do it. First, the 20 Newton force. Hope you can see it's got a line of action as shown there. The distance from the point where we're taking moments to the line of action is marked with the black arrow, and that distance is obviously in this case half a metre. So the moment of the 20 Newton force about point P is 20 times that distance, 0.5. And the moment of the 30 Newton force about the same point will be 30 times the distance from its line of action to P, which I hope you can see is 1.5 metres, 1 plus 0.5. So the total moment about P is obtained simply by adding them together. 20 times 0.5 plus 30 times 1.5. We've used the same point to take moments about, and we can just add the values up, giving 55 Newton meters, and both give clockwise moments, and the total moment is clockwise. Here's one for you to try. It looks the same, but if you look carefully, you will see I've reversed the direction of the 30 Newton force. So, can you find the total moment of those two forces about point P? Pause the video and have a go. Let's go through that. First of all, let's do the clockwise moment separately. The 20 Newton force produces a clockwise moment, as in the first question. It will be 20 times 0.5, 10 Newton meters. Because we've reversed direction, the 30 Newton meters produces an anti-clockwise moment. 30 times the distance to the point from the line of action, it's 1.5 meters, so the anti-clockwise moment is 30 times 1.5, which is 45 Newton meters. So we've got two moments, but they're in opposite directions. Now the biggest one is 45 anti-clockwise. Some of that is basically cancelled out by the 10. So to get the total, we've got 45 anti-clockwise and 10 clockwise. The total will be 45 minus 10, which is 35 Newton meters anti-clockwise. Now, it's very important that you understand what's on the screen, so if that's not clear, pause, read it through carefully, and make sure you have got the idea. Now, here's a little exercise to test if you understood. We've got 4 10 Newton forces acting as shown. That's the 4 arrows in the diagram, each is 10 newtons. Can you find the total moment of these forces about P? Pause and try that for yourself. Okay, let's go through it. Let's do the clockwise moment first. There's 2 clockwise moments to add. 10 newtons times 0.5 plus 10 newtons times 1.5. Yeah? 10 times half plus 10 times 1.5. That comes to 20 newton meters. The anti-clockwise moments are the lower forces pointing upwards on the diagram. They will have a total anti-clockwise moment of 10 times 1 plus 10 newtons times 4 meters. That's where we get those numbers from, giving 50 newton meters anti-clockwise. We've got to get the total, so we've got to combine the clockwise and anti-clockwise, and I hope you can see that the total will be 50 minus 20, which is 30 newton meters anti-clockwise. The overall direction is given by the bigger of the two, which is the anti-clockwise 50, gives you the direction of the final. Let's talk about sign conventions that we can use when talking about moments. We often use clockwise moments. We give them positive values, and anti-clockwise moments are given negative values. What does that mean? Well, let me show you the calculation we've just done. Hope you recognize that. It's just the problem we solved a moment ago. How would we do that using a sign convention for moments? Well, we'd do this. We'd say the total moment about P is, and we go round adding the moment of each force. So the order doesn't really matter. Let's do it left to right. 10 times 0.5, that's 10 newtons times half a metre is the first moment. We then add the second of the moments, which is 10 newtons times 1.5. That's the second term. Bottom left, we've got 10 newtons times 1. But it's producing an anti-clockwise moment, isn't it, that lower force? So it's 10 times 1, but because it's anti-clockwise, we use our sign convention, anti-clockwise negative, and we add minus 10 times 1. And the force on the right bottom, it's 10 newtons times 4 meters, but it's anti-clockwise, so we're going to add minus 10 newtons times 4. We do the arithmetic, and it comes to minus 30 newton meters. The minus sign tells us the overall direction of the total is anti-clockwise. Now, when we add these terms using plus and minus to indicate the clockwise or anti-clockwise sense, we give the sum a name. We call the sum the algebraic sum, or sometimes called the vector sum, of the moments. It's this expression here. We've added the moments. Some are positive, clockwise ones. Some are negative. Those are the anti-clockwise ones. And the overall sum of these 4 terms is called the algebraic sum. The term vector sum isn't actually technically correct, but you'll hear it used. It's best to call this sort of sum the algebraic sum of the moments. And before we finally talk about the principle of moments, what do we mean by rotational equilibrium? Well, we're talking about static systems at the moment. And let me give you a definition. An object is in rotational equilibrium when it is not rotating, not turning, not tilting. Simple as that. If it's stationary, it's in rotational equilibrium. Now later on, when you learn about dynamics, that's moving systems, you learn that rotational equilibrium means a bit more than this. It actually means an object is rotating at a constant rate. It's not speeding up or slowing down in its rate of rotation. And of course, a constant rate of 0 corresponds to not rotating at all. So for statics, stationary systems, by rotational equilibrium, we simply mean it's not rotating. Okay, Bear that in mind. Now, what is the principle of moments? Well, I'm going to give you a very simple version first of all, and then a more sophisticated version in a minute or two. Here's the simple version. If an object is balanced, the total clockwise moment about the pivot equals the total anti-clockwise moment about the pivot. I hope that is common sense. Let's do an example. There's an object, plank. Let's suppose it's balanced at its centre of gravity. The pivot is at the centre of gravity. What that means is the weight of the plank itself acts through the pivot and has no moment. So the weight of the plank doesn't alter the balance. So the only two forces we need to worry about are the one on the left, marked F, and the weight of the object on the right hand side, 10 newtons. And if the plank is balanced like this, we can draw the lines of action of those two forces. I could give you information about the positions of those forces, and I could ask you to find how big force F is. In fact, why don't I do that? How big is force F? Can you pause the video and try working that out for yourself? Pause now. Well, I hope you had a go. Principle of moments, this thing is balanced. What's a clockwise moment? Well, it's 10 newtons times the distance from the line of action to the pivot is 1.2. Clockwise, it's 10 times 1.2 newton meters. Anti-clockwise, it will be F times 0.6. So, from the principle of moments, we can write this equation down. Clockwise moment equals anti-clockwise moment. 10 times 1.2 was the clockwise. The anti-clockwise was F times 0.6. Then all we have to do is rearrange the equation. It gives us 20 newtons for F. Hope that makes sense. That's very important. Again, if it's not clear, pause, look at that very carefully. Now here's a rather difficult one for you, and it's difficult because I'm not giving you a diagram. I'm asking you to draw your own diagram. Let me read through the problem. A uniform 6-meter long plank weighs 100 newtons. A pivot is placed underneath it 2 meters from the left end. A box weighing 200 newtons and measuring 50 by 50 by 50 centimeters is placed on the plank, so the plank is balanced. You've got to draw a diagram including the forces and distances, and then you've got to work out what is the horizontal distance from the pivot to the center of the box. Now part B needs part A first. So your first task is to draw a suitable diagram with the forces and distances marked on it. Can you pause the video? Try that for yourself now. Hope you've had a go. Let me show you what the diagram should look like. There's a plank. It's uniform. It's 6 meters long. It's 100 newtons weight. You can mark the weight at the center because it's uniform, so the center of gravity is in the middle, and the center of gravity will be 3 meters from either end. The pivot's placed 2 meters from the left end. Let's mark that. Let's mark the 2 meters. It will be very convenient to mark a further distance of 1 meter, which is from the pivot to the line of action of the plank's weight. That 1 meter here. How do I know it's 1 meter? Because it's got to add up to 3. That distance is 2. If I take 2 away from 3, leaves 1 meter. Let's draw the box. 200 newtons weight. We don't exactly know where to put it, but a bit of common sense should tell you it's on the left hand side. It has to be to make the thing balance. You can mark the size of the box so we don't actually need it. That's your diagram. The other thing we could draw on is, because we know we're being asked for the horizontal distance from the pivot to the center of the box, it actually means the horizontal distance from the pivot to underneath the centre of the box. I hope that's clear. We could mark that, we could call it D, that's the thing we're being asked to find. We could mark that on the diagram. Now another thing that can make the diagram a bit clearer is to draw some alignment lines. I've drawn some there. So I've marked the left and right edges of the plank, that's where we're measuring distances from, a line through the pivot, vertical line, and the lines of action of the forces, the weight of the box and the weight of the plank. So those lines can make it easier to work out the distances or check the distances are worked out. So I hope you ended up with a diagram like that. The next part is to find out how big D is. So can you have a go and pause the video now? Well, how do we do that? Let me redraw the diagram a bit bigger. I've moved D, the arrow for D up a bit just to make it clearer. It's the same diagram. So, the thing is balanced. Let's use the principle of moments. Let's take the clockwise moments and say it must be equal to the anti-clockwise. Well, the anti-clockwise moment is that produced by the weight of the plank itself acting through the centre of gravity. It's 100 newtons times this distance from the line of action of the weight to the pivot, that distance, which is 1 metre. We were able to work that out. The anti-clockwise moment will be 200 newtons times D. We don't know D. So, total clockwise moment equals total anti-clockwise moment. That's the principle of moments for a balanced object. The clockwise moment is 100 times 1, and the anti-clockwise moment is 200 times D. All we have to do is rearrange that to find D, which comes to half a metre. Now, I haven't drawn the diagram very well. The box should have been nearer to the middle if it was drawn to scale, but that really doesn't matter. Okay, let me give you a better definition of the principle of moments. Two definitions, in fact. First one, if an object is in rotational equilibrium, not rotating in simple terms, the total clockwise moment about any point equals the total anti-clockwise moment about the point. Now, we don't need a definite pivot. We could choose any point we want. If the thing's not rotating, it doesn't matter what point we pick, it's not rotating about that point. So we can say in general that the clockwise moments about any point equals the anti-clockwise moments. It doesn't matter what point we pick. We'll pick a point that's convenient as a rule. I'll give you some examples in a moment. And an even better version of the principle of moments would be to say that if an object is in rotational equilibrium, the algebraic sum of the moments about any point is 0. So the positive values will exactly equal the negative values. The algebraic sum will add up to 0 if it's in rotational equilibrium. Let's use this. Here's a quite difficult problem. A uniform ladder rests against a smooth wall as shown. So look at the diagram. The yellow line is the ladder. The vertical white line is a wall. The top of the ladder is 8 meters high. The foot of the ladder is 6 meters away from the wall. The foot of the ladder rests on a rough floor, so there's friction on the floor, which is stopping the ladder sliding outwards. On the other hand, there's no friction on the wall. You're told it's a smooth wall. Now, our first task here, before we think about moments, is to identify all the forces acting on the ladder. Now, this is actually rather difficult, so I'm just going to tell you what all the forces on the ladder are. The first force is the ladder's weight, W. It acts through the centre of gravity of the ladder, which is in the middle of the ladder. How do I know? Because it's a uniform ladder. Any other forces? Well, if you look at the top of the ladder, there is the normal force from the wall, stopping the top sinking into the wall. I'll call that force H for horizontal, because it acts horizontally. What about the bottom of the ladder? Well, there's a normal force from the floor. I'll call it V for vertical. It's not sinking, the ladder isn't sinking into the floor, it's a normal force, the vertical supporting force. And the floor is rough, so there's going to be some friction which stops the ladder sliding. Excuse me. I'll call the friction F. It acts to the left and it stops the foot of the ladder sliding to the right. There's no friction at the top because it's a smooth wall. So those are the four forces on the ladder. So what? Well, let me tell you so what. I'd like you to try something. By taking moments about suitable points, decide if the following equations are correct. And there are 3 equations there. So, this requires some careful thought. Pause the video, read it all through for yourself, and try answering that question. Are those 3 equations correct or not? Pause now. Okay, well I hope you've had a go. You might have needed to copy the diagram out and draw some things on it. Let me go over the first one. 8H is 3W. The first thing to notice is that forces V and F aren't in that equation. Now, from what you know about moments, I hope you realise that if we take moments about the foot of the ladder, this point right on the bottom, V and F pass through that point. The lines of action pass through the point. The lines of action are 0 distance from the point. V and F have no moment about the foot of the ladder. So if we were to write a moment equation, V and F wouldn't be in it. Their values of moments are 0. So we can actually pretend V and F aren't there. What we're going to do is take moments about the foot of the ladder, that point at the bottom. What about force H? What moment does it produce about the foot of the ladder? Let's draw the line of actions of those forces. H acts horizontally. Its line of action is a distance. That's 8 meters, isn't it? 8 meters vertically. So the line of action of H is 8 meters from the foot of the ladder. The moment of H about the foot of the ladder is H times 8, 8H. The ladder is not rotating, it's in rotational equilibrium, so that must be equal to the anti-clockwise moment. H gives a clockwise moment, W gives an anti-clockwise moment. What's the anti-clockwise moment? Well, it's W times the distance of its line of action from the foot of the ladder, which is 3 meters, isn't it? It's half of 6 because it's symmetrical. It's in the middle, that centre of gravity. That distance is 3. The moment of W about the foot of the ladder is W times 3. And that's the first equation. 8H is 3W, just comes from taking moments about the foot of the ladder. And it's correct. What about the middle equation? Let's go back to all our forces. If you look carefully, the middle equation doesn't have H in it. That should tell you that if we take moments about the top of the ladder, we might be on the right track, because at the top of the ladder, H passes through that point. The moment of H about that point is 0. So we can forget about H if we take moments about the top of the ladder. Let's remove it just to simplify things. So, what are the clockwise moments about the top of the ladder? I hope you can see W is producing a clockwise moment. There's the line of action of W. How far is it from the top of the ladder? That line of action is 3 meters. So the clockwise moment is 3 meters force of W. That's a 3W. Any other clockwise moments about this point, the top of the ladder? Well, F is producing a clockwise moment about the top of the ladder. Line of action of F. How far is the line of action of F from the top of the ladder, that top point? It's 8 meters. So the clockwise moment from F is F times 8. So the total clockwise moment about the top of the ladder is 3W plus 8F. Now if the principle of moments is correct and the ladder is balanced, that should equal the anti-clockwise moment. What is the anti-clockwise moment? Well, it's produced by the force V. Line of action of V there. How far is the line of action of V from that top point where we're taking moments about? Well, it's 6 meters, isn't it? So the anti-clockwise moment is V times 6, providing we're taking moments about this top point of the ladder. And that gives us the middle equation. The final one, I hope you can see, doesn't have W in it. And I'm not going to go through it, but if you take moments about the centre of gravity, which is the middle of the ladder, you should fairly easily be able to see, using the algebraic sum of the moments, that the clockwise moments and the anti-clockwise moments add up to 0, and that these 4h, 4f, and minus 3v are the clockwise and anti-clockwise moments, and they must add to 0 because the ladder is in rotational equilibrium. So all three equations are correct. You'll note that we were able to take moments about any convenient point we wanted. You don't have to have a pivot to take moments. You can choose a convenient point to take moments about. Okay, well, we have finished that part. So I hope you found that useful. Thank you for watching.